Good afternoon and welcome back from lunch. I'd like to thank the organizers for the invitation and for putting together this combination of history in honor of Georges Lemaitre, fundamental physics, astrophysics, and astronomy. I've taken seriously the title of the workshop, and in my talk we'll be discussing all three elements of black holes, gravitational waves, and space-time singularities. Naturally, this leads to a certain amount of speculation, and I will try to clarify the extent to which various parts are speculative. Okay, good. By the way, this is not a spinning black hole. This is the Cassini picture of Saturn, but I like it because it shows a lensing, it shows an accretion disk, and of course it shows Earth in the background. Now, conventionally, the structure of a black hole in the textbooks takes this form of a singularity, in the case of a spinning black hole, a ring singularity, surrounded by inner and outer horizons and a static limit, sometimes called the ergo region. But is this really the structure of black holes? Is it all there is to the subject? And I think most relativists and particle theorists and quantum gravity experts would say, no, this is not what a black hole really looks like, certainly within the horizons. And to give some context of this, consider the statement of the great Chandrasekhar, reflecting on the beauty of the Kerr solution and the Schwarzschild solutions of general relativity, concluding that an exact solution of Einstein's equations provides the absolutely exact representation of untold numbers of black holes that populate the universe. Was Chandrasekhar wrong? Well, many would say so. And so I'm going to start my presentation with a little multiple choice quiz and ask the audience members to raise your hands if you agree with the following set of statements. The first one, which I've labeled as the astrophysicist version of the story. The Kerr solution correctly describes the universe outside the singularity and, well, inside in the very center and near the singularity within a Planck length. There are quantum effects that we don't attempt to describe in general relativity. So this is the conventional view and one that Chandrasekhar's statement certainly represents. A more recent version of this story, coming from classical general relativity theory, is that the Kerr solution really only works outside the Cauchy horizon for reasons that I will describe later, and that the singularity structure is modified inside, but still can be described by Einstein's general relativity theory to a high degree of precision. Of course, in recent years, quantum gravity and string theory have given us a very different concept of black holes, including the idea that a black hole is not empty space with a singularity in the center, but rather a quantum fuzzball, according to Samir Mathur at Ohio State University, or perhaps even something as dramatic as a firewall around the event horizon, which would completely modify the classical description of the black hole. Of course, none of the above is a perfectly good option. So I won't ask for a show of hands, but you might mentally make a note of which of these categories, or which several of them, do you fall into. Quantum superposition is, of course, allowed, perhaps with entanglement entropy in this room. Now, how is this related to Georges Lemaitre? Well, as has been mentioned this morning, Lemaitre, of course, produced several exact solutions, descriptions of the field equations of cosmology. And the Lemaitre-Tolman-Bondi solution, as we describe it now, was Lemaitre's. And in fact, Lemaitre's model describes not only a cosmological model with cold dark matter, but it also describes the collapse of pressureless matter to form a black hole. And that underlies the solution of Oppenheimer and Snyder for the first realistic gravitational solution of Einstein's equations showing black hole formation back in 1939 for a spherical black hole. The second reason to cite Lemaitre here is his boldness in advocating the cosmological constant as an addition to general relativity. Nowadays, of course, we are happy to add many terms to the classical gravitational action, including R-squared terms and higher powers of the Ricci scalar. There's a whole class of cosmological theories called F of R theories. And so it's very sensible to ask, in the context of black holes, what do F of R theories mean for the black hole structure? In outline, my talk will consist of three somewhat separate topics, but they are all related through black hole physics. A review of the Kerr geometry and its limitations. That was kind of how I began this talk. Some very interesting and exciting recent work on the use of gravitational waves to explore black hole geometry. And then going back to a question really of classical relativity and geometry about the Kerr black holes themselves. Right. So the Kerr geometry. Conventionally, we represent black hole geometry using conformal diagrams or Penrose diagrams on the left. We saw some of those earlier in Vidotto's talk. So these are diagrams in which the light cone geometry of special relativity is preserved through two coordinates, one time-like coordinate and one radial coordinate for those geometries that have a sensible radial coordinate. The Kerr geometry has many replicas of large sections which become asymptotically flat along future and past null infinity on the sides, and then connected by some more interesting structures with wormholes through which one can imagine taking a time-like path, so a path that moves from bottom to top in the diagram of an observer who manages to avoid the singularities at r equals 0. Of course, with the Kerr solution, r equals 0 is a ring, and it's in a coordinate system such that the entire disk interior to r equals 0 is also r equals 0. There are additional coordinates, polar coordinates, that govern the geometry, and those will play a role. So this is the conventional representation of the Kerr solution. The Kerr solution is static and eternal. So there are infinitely many copies in the t direction here. To go into this in a little bit more detail, each of the patches of the Kerr solution can be covered by a coordinate system. Black hole solutions are examples of spacetimes where you need more than one chart to cover the manifold. So you need multiple copies of the coordinate systems. And there's a conventional way of doing this using Kruskal-Sakaris type diagrams and coordinates, or Kerr-Schild type coordinates. And the important thing here is to notice that there are 45-degree lines. These are horizons. So a photon world line can skim a horizon. And there are horizons at two different angular radii in the metric called r plus and r minus. The larger one is called the event horizon. The smaller one is called the Cauchy horizon. And there are different sections of these coordinates that you can patch together, describing the spacetime outside of r minus or inside of r plus. Putting those together, the bottom diamond shape and then the top lozenge shape, for example, allow you to make connections and to build up what's called the maximal extension of the Kerr solution. The one technical point here is that I'm only showing a portion of these lozenges inside of the Cauchy horizon because the conventional view is that the Kerr solution actually continues beyond this r equals 0 line, and I'll come back to that towards the end of the talk. Okay, so that's summarizing what I've said in words. Now, at the beginning, I suggested that the astrophysicist's conventional view was that the Kerr solution accurately describes black hole physics away from the singularity. That can't possibly be true. The Kerr solution is eternal. The black hole has always been there, and just like in the Schwarzschild solution, there are multiple copies. In the case of the Schwarzschild solution, as you may know, this leads to a white hole in what's called the maximal extension of the Schwarzschild solution. Simply put, if you had only this upper right-hand portion of the space-time, you could draw geodesics which would come to an end at the geometry, not on a singularity. That shows a property called geodesic incompleteness, and to complete the manifold with the metric, you have to make a second copy, and that brings in the presence of a white hole. This is not a physical geometry for a black hole that forms at some point in the past. It could be a model for a universe that has a white hole making a transition to a black hole. Of course, we heard the talk before lunch about the reverse, a black hole making a transition to a white hole. So the more proper diagram, conformal diagram for a black hole that forms by gravitational collapse, in the case of a spherical, non-spinning, non-charged black hole, has a section of an asymptotically flat space-time, and then with the surface of a star, which collapses toward r equals 0. R equals 0 is time-like until the singularity at the end, where it becomes a space-like surface. And there is a 45-degree line here, which I've not shown you. That's the event horizon. Once the trajectory crosses that, then causality means that the matter is forced to move inwards towards the singularity. So we can easily conclude that the simplistic description of the black hole as being the Kerr geometry everywhere and always is obviously false, but it raises the question, which of these description is then correct? Or, put another way, what is the conformal diagram of a spinning black hole formed by gravitational collapse? Well, there are conjectures from classical relativity. Let me say this is a difficult problem. Nobody has ever constructed an exact solution of a spinning black hole that forms by gravitational collapse, nor are there good numerical solutions which describe all the physics across the pairs of horizons that form. But there are very good physical arguments that modify the structure compared with the full Kerr solution or with the Oppenheimer-Snyder collapse solution in the following ways. So first of all, that event horizon is there. Now I've drawn it in. But instead of the solution terminating at r equals 0 here, there are several modifications of the singularity structure above. So the first is that this Cauchy horizon is where a phenomenon called mass inflation occurs that was discovered by Poisson in Israel in 1990. What happens is that streams of matter that enter into the black hole and pass through the singularity and back out again, counter-streaming streams, have a very large stress, as in the sense of a velocity dispersion from those counter-streaming bits of matter or radiation that have fallen into the black hole before. And of course, we know in the context of cosmology that a large negative pressure modifies the geometry. The same is true within a black hole, and the result is a phenomenon called mass inflation that was diagnosed by Poisson in Israel, and it makes this null surface actually singular. The curvature diverges there. There is a second null surface, which is a different Cauchy horizon in the Kerr maximal extension. If you take a world line outside of the stellar surface, then in the full extension of Kerr geometry, you could actually exit to two different universes. And in this case, both of them have these curvature singularities. This has recently been called a shock singularity by Maroff and Ori, and it's a somewhat weaker singularity in that although the curvature diverges, the integral effect of passing through that Cauchy horizon does not tidally disrupt a body. It's a weak singularity. And then at the very center of the black hole, the modern thought is that the singularity is not static, but actually is oscillating very rapidly and chaotically in what had been called a mixed master universe by Charles Misner in the 1960s, and now we call it BKL singularity after Belinsky, Kalatnikov, and Lifshitz, who described mathematically the physics of that singularity in some care. And these ideas have been sketched out in a number of papers recently, for example, this one by Burko et al. So from the point of view of a classical relativist, this would seem to be a plausible description of the curved geometry, and the rest is some details of working out the exact structure of those singularities. I stress this is still somewhat speculative. We have no full numerical models that validate this picture. And we also have very good physics reasons to think that the black hole structure should be modified. We've already had reference to Hawking radiation and black hole evaporation. I'm not going to talk about black hole explosions. So quantum fields lead to Hawking radiation. This causes an information paradox that the entropy of the outgoing radiation we seem to have lost some information. We have to worry about the unitarity of the quantum theory. And that has led to various schemes for resolving this paradox that may imply that quantum gravity modifies space-time on scales much larger than the Planck length. And in particular, there are many such proposals, but two of them that seem particularly dramatic to me from the point of view of classical relativity are the fuzzball of Matur and collaborators and the firewall of AMPS, Polchinski and company, that we heard referred to earlier. And I say those are dramatic because they impinge on the classical structure of the black hole, modifying the geometry as far as, or maybe even beyond, the classical event horizon. And if so, that suggests that they may be amenable to observational test through gravitational waves. So that's what we're going to look at next. So I get to be the first person in this workshop to show you the LIGO results for the beautiful gravitational wave signal of coalescing binary black holes. I'm sure everyone has seen this diagram of the gravitational wave strain measured by two detectors in the United States, here shifted and superimposed to show you the good match. The reconstructions, the famous chirp of the gravitational wave frequency versus time over a couple of tenths of a second. Now, the point is that this is, in principle, offers a test of general relativity because the templates are constructed using general relativity, and a different theory might yield different templates. Now, the whole notion here of using gravitational waves to study the physics at or within the horizon seems counterintuitive. And you may well object that there's no possibility of using the waves emitted from outside the horizon to probe the physics inside the horizon, so surely, therefore, we can never test the firewall theory or maybe even the fuzzball theory. I disagree. If the black hole geometry is modified by some quantum physics or classical physics, then the Einstein equations no longer provide the full and complete description of the geometry outside the horizon as well as inside. And in particular, in the very dynamical space-time of colliding black holes, then you will have differences arising in different theories that enable an observational test. So this is an indirect way to probe the full physics governing the black hole collision. And there can be some very surprising predictions and maybe even more surprising deductions from data. So in a recent paper, Betty, Dikar, and Afshordi did a rather bold thing. They analyzed the full gravitational wave signal from LIGO, from three black hole mergers, and here they show a fit to the strongest gravitational wave source that we've seen so far, which was the original binary black hole collision from September of 2015. And what they showed is that there is some, I would say rather weak, but still very interesting suggestion in the data. Here I'm not showing the full data, but only their fit, of actually having some repetitions at a reduced amplitude of the original in-spiral and coalescence waveform. They call these echoes from the abyss. And their motivation was a toy model of something like the firewall, in which there's some kind of reflection of waves between us. And they treated as a reflecting surface outside of the horizon, and then what they call an angular momentum barrier, or some kind of outward layer. And there's been criticism directed at their work from both the theoretical and the empirical approach, and I acknowledge this paper is not without its defects, but one of its great charms is a very bold test of relativity that can be done independently of models. Just look for such signals. General relativity should not, we think, predict any kind of a repetition or echo of the gravitational wave signal. And they claim a 2.9 standard deviation result. Not enough to convince the skeptic, but as we heard this morning, perhaps it would have been enough several decades ago. So that's fascinating, and it's an example of how we can use gravitational waves to test some rather serious departures from general relativity. Now, the fuzzball and the fireball models are not at this stage able, to my knowledge, to make such quantitative predictions. But there are other descriptions of black hole structure, such as ones based on F of R theories, or in this case an R-squared gravity model of Sibanza et al., that can. And perhaps in the Q&A I'll say a little bit more about that. But I want to spend my last 5 minutes on a different question, one that goes back to the original black hole model. So I'm not proposing this as a realistic description of a black hole. It's a somewhat academic one of asking what's the correct maximal extension of the Kerr solution? Is the maximal extension that's in the textbooks unique? So this is work that I did a few years ago with a summer student currently at Princeton. And it brings in the very important concept of topology, which has been implicit in some of the discussion before, and I'm sure will become explicit again. Very importantly, the metric does not fully describe space-time. The metric is certainly not enough to fully describe a space-time. You need the topology of the space-time. You need the range and periodicity of the coordinates, the connectedness of the manifold, and so forth. And I already alluded to the topology of the Schwarzschild solution as an extreme example of that. So with the Kerr solution, the maximal extension that was written by Boyer and Lindquist in 1967 leads to a region of the space-time with negative values of the r coordinate. There's nothing wrong about that. The geometry certainly can have r less than 0 in the particular coordinate system that is used. And remember, r equals 0 here is not a point. You don't go to r equals 0 and then end on a singularity. You can go through r equals 0. It's a full disk as long as you avoid the rim of the disk. And then passing through that disk in the Boyer and Lindquist extension of the coordinate system, that leads you to r less than 0. If you think about something like the Schwarzschild solution with r less than 0, remember at large distances you have a weak field limit in which there's a gravitational potential minus gm over r. Well, that's now changed sign, so it becomes a repulsive force. So a lot of the physics of motion in that metric changes dramatically, and in particular there are closed time-like curves present owing to this extension, as was shown by Brandon Carter in 1968. And this is the figure from the textbook from Hawking and Ellis, which shows the matching of the coordinate systems to the extension r less than 0. The student and I think that there is another matching, which depends on some subtleties of the polar coordinates, and I won't illustrate it here using the oblate spheroidal coordinates, but I'll simplify it with just a description of the polar coordinates in the plane. And the question is, how can you glue together two Euclidean planes into one connected surface? avoiding, of course, the coordinate singularity at the center of the polar coordinates. It's evidently a coordinate singularity of these r and phi coordinates. And one way, which corresponds to the Boyer and Lindquist choice, is that as you cross through r equals 0 here, you continue along the same angle. But you can see I can do that if I rotate my angles in this way. And now my coordinates are completely continuous as I pass through r equals 0. As I change an affine length, an affine parameter along such a trajectory, r changes smoothly and so does phi. Okay. But that's not necessary. The polar coordinates are arbitrary, and I can certainly choose a coordinate system in which the second copy has the same orientation, and now phi jumps by pi over 2 from 60 degrees to 180 degrees as a result of a coordinate artifact, coordinate singularity. Okay? And the thing about this is that in this description, r is greater than 0. This is just the conventional polar coordinates. So if you can have a discontinuity in one of your angles, you can avoid going to r less than 0 in the extension of the Kerr metric. That's what we have concluded. And so passing through the central disk, r equals 0 disk of the Kerr solution, rather than r changing sign, r might be positive on both sides, but with the angles being discontinuous, so that the gravity remains attractive rather than repulsive. The angles jump. There would be no closed time-like curves. In both cases, there are Cartesian-like coordinates that are continuous across the disk. So our conjecture is that there may be a different maximal extension of the Kerr solution which avoids the closed time-like curves and therefore modifies a little bit the description of the Kerr geometry from what is understood. However, that doesn't change the conclusion that this still should not describe a physical black hole because of the other physics that I mentioned of the streaming of fields across the horizons. So to summarize and give conclusions, the Kerr geometry, certainly the full Kerr geometry, cannot describe black holes. Whether you want to choose a quantum description of black holes or a classical or semi-classical description of black holes, maybe that's something we can discuss at the end of the afternoon. But regardless, this is still a somewhat mysterious area because we have no exact solution. We don't even have good numerical solutions to be sure of even the classical solutions of the Einstein field equations for the formation of a spherical black hole. However, we do have a powerful new probe of black hole geometry, and the very idea of Abedi et al. That you could actually test for the existence of reflected waves is pretty amazing, pretty astounding that we can test something so fundamental as the horizon structure using gravitational waves. And then finally, do Kerr black holes imply the possibility of time travel? Not necessarily, but this, I would argue, is academic because the solutions can't fully describe a realistic black hole anyway. So thank you for your attention, and I'll take some questions now.